So what is Coulomb's law anyway? So let's begin by considering two charges, one charge little q and another charge big Q, separated by some distance r in between them. And there's some force on big Q, which is pointing away from little q. So let's talk about the magnitude of that force. So we learned in introductory physics that the magnitude is k little q big Q over r squared. Or we can write this as 1 over 4 pi epsilon naught q over r squared. And we're actually going to use this form of Coulomb's law throughout this course because the form using epsilon naught is going to be more useful for us. And this epsilon naught quantity is just known to be 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. It's called the permittivity of free space. It's one of these fundamental constants that will show up a lot in electricity and magnetism. So that's the magnitude of the force, but we can also talk about the vector direction of the force. So in vector form, we write the force on big Q as 1 over 4 pi epsilon naught little q big Q over r squared in the r hat direction, where the r hat direction points away from the other charge. And r hat is a unit vector, and so that means its magnitude squared, which is just a dot product of r hat with itself, is just 1. So again, this is pointing away from that charge. So we usually call little charge a source charge, and then big Q is the charge that we're interested in the force on. But of course, this form of the Coulomb's law assumes, and it implicitly assumes, that little charge q is actually at the origin. But that need not be the case. So, for example, what if we consider both of the charges to be not at the origin? So we have a set of axes, x, y, and z, and we have a little q1 and a little q2, which are not at the origin. We can describe where they are by a vector, little r1 vector and little r2 vector. And then we talk about the separation between these two with a vector called the separation vector. And we use this script r notation for it. It's oftentimes also called curly r, and usually we're just going to call that curly r. So the magnitude of curly r tells you the distance between q1 and q2. So it's the generalization of the little r that we had before. And you could also talk about the direction, curly r hat, which is a unit vector and points in the direction of curly r, so it points in the direction of the force. So using this curly r notation, we can write Coulomb's law in a new way, and in fact in a more general way. So it's not really a different Coulomb's law, it's the same one, just much more general. And that is that the force on q2 here is equal to 1 over 4 pi epsilon naught q1 q2 over curly r squared curly r hat. Okay, so the last thing I want to mention about Coulomb's law then is the principle of superposition. And the principle of superposition says that if you have a lot of different charges hanging around, say 3 charges q1, q2, and q3, and they're exerting forces on some other charge, big Q, then you can consider the individual forces, F of q1, F of q2, and F of q3. And of course, like all forces, these forces will add together vectorially to give a total force, a total net force. And so we're just going to say that the total net force on big Q is just the sum of each of these individual forces, dot, dot, dot. And so we can write this out in a little bit more detail, little q1, big Q over curly r1 squared, curly r1 hat, and so on, where curly r1 and curly r2 represent the curly r's for each of these individual charges.